Yeah, Shivani, we will do this together because it's a new tool, and we thought it's probably easier if we're here together, so that we keep the pace appropriately. Yeah. All right. We have a short, or we will start with a few slides. Very quick wrap up, maybe, of what I ended yesterday.
Yes.
So you have seen that I have introduced Equilib. You have seen that Equilib is very good in terms of no program knowledge and also results visualization. You have a lot of flexibility of what you plot for small processes, or small equilibrium calculations. In the end, that describe then your system in a very small local position. But then powerful advanced use, we wrote no here. Model visualization, it's not really for process modeling anyways. This is for calculating equilibria in some positions. So of course, there's also no model visualization. And then support for iterative processes is partly there, but not in the same level as you will see it today. And also scalability is not really given. Very quick wrap up again of the process that we want to cover now in this demonstration. So we start with the LD converter, where we have 4 different input streams entering the converter. And we say we have 3 output streams that leave the converter in the end. Some of that slag might be carried over, as we have learned yesterday. And then we have the ladle metallurgy with alloying, degassing, and the desulfurizing, again, with many input and output streams. And if you work with a real system, you probably want to optimize these streams in a way that you can recycle cheap scraps, for example. There will be one example that we will introduce later. Shivani, please introduce us to how to get started with FactFlow.
All right. Okay. So first of all, good morning, everyone. And I'm very thrilled to demonstrate FactFlow demonstration also with Moritz today. So FactFlow is very simple, interactive, and flexible software. You can visualize your process. You can also design your process and also optimize your process, all in FactFlow. The purpose of today's demo is that to show features of FactFlow, and also you can see how this tool might be applicable for your process. So I will have to wait. Okay. So first of all, how do you wait? So how do you start FactFlow? So you go to FactSage 8.4. Then add-ons, because FactFlow is an add-on, and you can click on FactFlow process simulator package, and then you click on run, and then you have very nice FactFlow window opening. You can create a new project or you can search a new project. So I will create a new project. I would call it mini. Right. So this is the interface of FactFlow, how it looks like. On the top, you see there are some options. There is a run button on the top left corner. There are process model units. So basically input, output, you can split your streams, you can mix your streams, and also you can calculate the equilibrium process using equilibrium reactor. In the bottom, you see the summary of the whole overall project here. You see that I have not selected any CSV file yet. And all these model blocks are called as nodes in this that we will also see today. And you can also plot your plots in FactFlow. On the top, there are several units possible for temperature, pressure, and energy and quantity. Also, you can see the stream text I will show you today, and also you can vary alpha parameter. So Moritz.
Okay, yeah, thank you, Shivani. I understand we have to start with the data file selection, right?
Right.
And
okay.
Remember, I introduced you to that. I prepared you already for that yesterday.
Yes. So
how do you do that?
Yes, so I have created a CSV file already, but I will show you how you can create your own CSV file. So you will go to Equilib, you go to Files, and then you go to ChemSage file, and you will export it as transparent CSV file, which is compound solution template file. And this is the file that we need for FactFlow, FactProSim, and ChemApp for your process simulations. So I have it all created basically for today.
Okay.
Okay. And you see, this is the CSV file I have loaded.
Okay, good. Then let's start building a process. So we will start with a simpler example, not the full flow sheet. We don't build that live. But let's start with just the iron, carbon, hot metal, and then the oxygen that we blow into this pig iron.
Okay.
Okay, so you have dragged already one input stream.
Right.
Okay. What are you doing?
I don't know.
Really?
Some button is getting clicked.
Oh, okay.
Okay, so this is hot metal, right? Okay, I have to remove that one. Okay. So this one is the first block that we have taken. It is at 1300 degrees, but this is in Kelvin. So
change your unit.
I can change the units. I have to hide this. Okay, so I can change the unit to 1300 degrees. I have pressure 1 atm. And what do we, so these are all the phases that we have in the CSV file.
Again, complexity of chemical space. Unfortunately, that is a given, right?
Right. So what we want is that in the iron liquid phase, we want how much
let's take
iron?
96 weight% of iron and 4 carbon.
Yes. So I will take 96 and carbon is 4. Right.
Probably. Okay. You have the relative tick box there and the quantity.
Yes, I can also take 100.
Okay. So you can input absolute amounts or you can put relative amounts.
Yeah.
To
Both are
specify
possible.
the composition. You have already dragged on a new input stream.
Right. Yes. So what would you like to have here?
Let's take oxygen, right?
Okay. O2. And you want to have it at room temperature?
Yep.
Right. Okay. Then in the gas ideal, you can select oxygen.
This is a long list. How do I manage such a long list?
Yeah. Yes, then you can select only active species. So I have selected only oxygen, then you only see what you have added. So I have taken 100% oxygen and maybe let's take 6 tons about oxygen.
Okay.
Right. Okay.
Okay, now we have 2 input streams, but we want them to react with each other, right?
Yes.
So
for that, we will take Equilib reactor. So maybe I will write the name of the. Okay. And this is at what temperature?
1600 degrees Celsius.
Okay, so the solid is the output, the white is the input. So we connect these 2 input streams into the reactor. And we want some outputs as well, right?
Yes. Can we also add a splitter?
Okay.
Yeah. Okay, so the splitter, as you can see, has 1 input and 2 different outputs. You can also change that. But here we probably can only work with 2. Let's split into gas phase and condensed phases.
Right. Okay. Okay.
So you're building up the flow sheet, and as you see, all of the flow sheets, both here and also in FactProSim later, you should always read from left to right. Yeah. Okay, what are you doing here?
So I'm splitting only the gas to the first output, and I am splitting the solid and liquid phases to the second output, which is the condensed phase here.
Okay. Yeah. Okay. So you see that this is a table where you can, this is out one, which is the upper one, out two, the lower one. 100% of the gas should go to out one, 100% of the condensed phases to the out two.
Yeah.
Okay. Nice.
Right. Okay.
All right. Now we have set everything up already, right? Is there anything else we have to do?
I don't think so.
I think we can click run.
Okay. So we can run the process.
Okay.
And you see it's very fast.
Okay, but it's also a small data file.
Yeah.
Yeah. Okay, and you can see that there is all of the results are displayed immediately. This is nice if you work with it actively. This is not so nice for a demo. So maybe let's switch that off. Less complexity. Okay. Good. But can you show how we can analyze results
Right.
a bit?
So you can go to reactor and then you click, then you right click on it, then you see the results.
Okay.
Yes. So these.
What do we see on the left and on the right?
So on the left, we see the input, so which is the hot metal that we have added, and also the gas and their amounts and the phase. And the similar things you can see on the right, how much of each of them we are forming, the amount, and yeah.
Okay.
Yeah.
Okay. Good. So we form 96.14 grams of liquid, and that makes probably sense.
Tons.
Tons. Sorry.
Yeah. So yeah.
Yeah. Can you extend the Equilib so that we see the composition?
Right.
Okay. So we have 95.9985, so nearly all of the 96 tons of iron that are still in the liquid. A little bit will be probably in the gas phase. And then we have now more oxygen than carbon that's dissolved in there. Okay.
Yes.
Nice. Shall we introduce alpha?
Okay.
Let's do that. Okay. This is now a fixed oxygen amount, right? So let's introduce a variable oxygen amount because, of course, you want to vary some amounts usually. How do you do that?
So you can add alpha here. So, and then you basically vary your amount. How much?
Then you have to remove the relative, I guess.
Yeah.
Okay. Yeah. Okay.
Then you can set, I don't know how much you want to vary.
The 6 tons was already too much, so maybe 0 to 6 in steps of 0.5.
Okay.
Okay, notation. Do you want to quickly explain that?
Yes. So this is very much like Equilib. So you put the lowest point, and this is where you want to reach the highest point, and this is the step size basically. So this is very similar to Equilib. What is different is the alpha notation. So this is 1 into A and not inside the bracket A.
Yeah, and the underscores that you have to add there at the top, right? In Equilib, it's just a space.
Yeah. Yeah.
Okay, good. That's it.
Yeah.
Then I would say let's run. Okay, I don't know whether you could see that there was a blinking
green
box. Yeah, this is one equilibrium calculation. Sorry, direct question. So this is the alpha.
No, so I write A, but it transforms it as 1 into A.
Yeah.
Okay,
let's make a plot.
Okay.
Let's look at carbon concentration in the liquid iron.
Okay.
As a function of alpha.
Right. So again, I right click on the results and then I go to Equilib phases. And then I can again right click and I can also plot analysis. And you can see, so this is alpha. So this is increasing oxygen basically. And you see that the carbon in the Equilib phase goes down significantly. So, and which is what we want to do. So, yes. So this is how you can also create plots.
Okay, nice. Yeah, and you can see that you can also, I guess you can save them also.
Yeah,
right?
you can set them. This is oxygen amount. This is, So
I think that's fine. But
okay. So
if you could just scroll down on the right.
Yes.
Yes. Okay, there's export to Excel, to CSV and also
you can.
Yeah. Okay.
Okay.
Excellent. Is there anything else on this part?
Just I wanted to mention, like we added from our own carbon and iron, but actually in your actual process, what you see, so you can get chemical analysis from your samples. So using EPMA or ICP-OES, so you can also introduce your experimental details into this process simulation software, so you can get real insights from that.
Okay, good. All right, then let's go to the advanced use. Sorry, Alex. Question just for the online audience, is it possible to fix activities? No, this is not possible. You can only work with isothermal reactors, and you cannot fix activities.
No.
Yeah, sorry,
Okay.
Another question? Yeah.
Yes. Yes.
Yeah.
So we just calculated
let's quickly repeat the question. Can you add or remove heat in the equilibrium reactor was the question. Yes.
Can you add or remove heat?
Heat losses, yeah. So you see that you can input the temperature of the reactor.
Yeah.
And you get as an output the heat balance, but you cannot input and enforce a heat balance. That is something you can do with with FactProSim, as you will see in an hour. Yeah. Okay. So then we go to the more advanced case. Yes. And you have prepared that already. So maybe you can quickly guide us through this, because this, of course, if you have such a complex process that you want to model, the flow sheet will be more complex as well.
Right.
So and you have zoomed out already.
Yes.
So please zoom in.
Yes. So before I zoom in, I first wanted to give an overall picture. So this is the steel making process, presentations of which we already saw, but a quick revision here. So there are 4 parts in this process. So the first part corresponds to the primary steel making, and this happens in the BOF furnace. The second, third, and fourth part, they correspond to the alloy addition, degassing, and de-sulfurization, and they all happen in the ladle furnace. Okay, now we can zoom into maybe...
Yeah, maybe you quickly start with the first one.
Right. Okay, so first one. So one thing to note that in this flow sheet, all the inputs are at room temperature except the hot metal, which is this one, and all the reactors are at 1600 degrees. Okay, so we have hot metal, oxygen, scrap, and calcium oxide as flux, and they all go into the converter. You can split the stream easily in FactFlow, so you can have off-gas, slag, and this stream, which contains a reduced amount of carbon, as we just showed before. And basically, this is the steel stream. From this point on, the steel stream will then be transferred into the ladle furnace, where alloying will be done, and also some part of deoxidizing. So you see here, okay, so you see here that there are several alloys that can give some desired properties to your steel composition. They can part composition of the steel, and also you can add deoxidizers. So aluminum is a great deoxidizer because it can form Al2O3, and that will go into the slag. And again, here we split the stream, and then we have at this point the steel stream that goes forward to degassing.
Okay. Maybe because of time, let's.
Okay.
I mean, then there is the degas, so there's a desulfurizing at the end.
Yeah.
That's probably enough.
Yeah.
I guess everything is set up already. All the split factors are defined, so
everything is
we could just run, right?
Yes. Okay. So we can run the flow sheet. Yes, but do you want to run with the...
Okay, yeah. Okay. Yeah. So we thought about what could be a nice small case study that we can demonstrate. And we have thought about, okay, let's assume that you have 2 different scraps that you can mix. One scrap that is more or less pure iron, and another one that contains titanium. and you want to know whether the titanium would be ending up in the final steel. Yeah. So how do you do this? How do you define a variable input?
Right. So originally in the initial example, what Moritz showed yesterday, we had 18 tons of scrap. So I have modified it to, yes, so I have modified in steps of 0.25 to add maximum 1 ton of steel in this process. And you see this is, again, titanium is a variable A, and the iron BCC is then 18 minus 1 into A. So this is a bit different than in the Equilib. Yes, and we can do it. So I can run it if you want.
Just quickly again, so we will have up to 1 ton of titanium that we add into the scrap. Yeah, and we will see what will happen with that. Run it.
Right. Okay.
Okay, you see now that the blinking of the blue, sorry, of the green
Yes.
line is a little bit longer.
Yeah.
Because we have a more complex data file, and of course, then calculations take a bit longer.
Yes, and also on the right top right, you can see which alpha it is calculating at this point.
Okay. Yeah. And what we want to do next is we want to plot the final titanium that we have in the steel.
Right.
And we want to compare how much of the 1 ton, up to 1 ton of titanium that we had in the scrap is recovered in the final steel.
Okay.
Okay.
Okay. So in order to do that, we will go to the final steel where it is found, which is in de-sulfurization reactor process. So I will again right click here to go to the results, and here, yeah. So you want to plot titanium?
Yes.
Okay. So titanium, I can click again. I can plot analysis of titanium, and this is the amount of titanium in scrap, right?
Yeah, in tons, maybe you add tons as a unit.
And this is quantity of titanium in refined steel. Right. So as you see, as we increase the amount of titanium scrap, basically, the more of it is recovered, but it's still a bit.
Yeah, if you compare the absolute amounts, 1 ton on the x-axis and the maximum on the y-axis is 0.04, so 40 kilograms. So of course, the more titanium you have in the scrap, the more titanium will end up in the steel, but still 96% of the titanium is lost in the process, right?
Yes.
Yeah. Okay. Yeah. I guess that was in the end the final part that we wanted to demonstrate. It is possible then to see what effect a change in the very initial part will have on the final part, of course, under a number of boundary conditions. Yeah.
Yeah. And you can also vary your temperature, pressure, amounts, and basically, in principle, whatever your process conditions are, and very fast see the impact of what it will have on your entire.
And just one more comment. How long did it take you to, or how long would it take you now to build this flow sheet again from scratch?
I think this big one, you mean? If I have all the data, maybe like a half hour. It's not so much, no.
Yeah. Okay. And that is, I think, the real benefit. Yeah.